great. I hope you're all fed. So Sebastian Schweighofer-Kodritsch will give the next talk. Take it away, Sebastian.
Okay, good afternoon, everyone. It's great to be here. I'll now be talking about obviousness around the clock, which is joint work with Eve, who's also with us. So let me start with some general background. I think in recent years, mechanism design, in particular market design, has received some increased attention from a behavioral perspective, and that has revealed that even strategy-proof mechanisms often do not work so well. So two examples of that would be one from the field, a high-stakes decision, the US medical residency match, where it's now well documented that a lot of medical students misrepresent their preferences trying to strategize in strategy-proof mechanisms where the dominant strategy is to truthfully report your ranking. Another very different example is very old, goes back to the 80s, where Kegel, Harstad, and Levin have shown that the sealed bid second price auction, where it's a dominant strategy to bid your true valuation in a private values context, they have shown that the sealed bid second price auction leads to severe overbidding, and that also defies learning. Whereas the theoretically equivalent ascending clock auction, people very quickly figure out that it's best for them to stay in up to the point where the clock price reaches their valuation and then drop out. So this is challenging to theory because of all these mistakes. They could not be due to the kind of well-known difficulties that behavioral game theorists have focused on, that are due to difficulties in mistakes due to difficulties in strategic or equilibrium reasoning, because people have a dominant strategy here. So something else must be going on. And then a few years ago, Sheng Wu proposed an answer to the question what the issue is, and also a fix, so to speak. So the basic idea, I would say, is that recognizing dominance is not so easy because there can be a lot of contingencies that you have to distinguish. So it requires some contingent reasoning in terms of what others might be doing, and you need to go through all of these contingency by contingency to see that this one strategy actually does better than anything else you could do. And probably it's easy to get confused there. Importantly, so it provides a formal definition of when dominance should be obvious from the extensive game form or from a mechanism in a way that it relaxes the contingent reasoning requirements for recognizing dominance. And based on sort of this notion of obvious dominance, he proposes a selection criterion called obvious strategy proofness, so that whenever it applies, we sort of should use this criterion to select those strategy-proof mechanisms where dominance is actually obvious to people, which would avoid any sorts of mistakes, and so that promises huge welfare gains. Moreover, he also provides his own lab evidence that this actually has behavioral content, and it does what it's supposed to be. So he replicates this old finding on auctions, which sort of supports the theory, because the sealed bid second price auction, which is here 2p, is not obviously strategy proof, whereas the ascending clock auction is obviously strategy proof. There's also another comparison that also provides overwhelming support, which is on random serial dictatorship mechanisms, and we'll hear more about that tomorrow, as I saw in the program.
How is that evidence different from the evidence from the 80s? It seems to be the same.
It's exactly the same evidence. This is a high-powered replication of the 80s study. So what do we do in our paper? More detail is to come, of course. So we revisit this auctions evidence with private known values. So first we'll argue that this evidence is subject to some potential confounds of theoretical obviousness in terms of design differences, where these confounds may be of independent interest for a designer designing auctions or more generally mechanisms. Then we sort of provide an experiment that quantifies these confounds that are related to sort of how feedback is given, also some kind of irrelevant information, and also isolate a key requirement of theoretical obviousness, which is sort of to bid dynamically. And we do so by comparing not just 2P and AC, but we add a set of auction formats in between those two, to isolate, to zoom in on the design differences and see the effects of these differences on behavior. What we find is that the significantly superior performance of the ascending clock auction is almost entirely due to those confounds, and we can discuss what this means about the theory, or in what sense these are confounds. And finally, we also add a structural analysis of bidding behavior, as it relates to actual material incentives, that tries to look deeper into how design actually affects behavior, not just how close you get to dominance, but also what kind of mistakes people make. Okay, so let's start with bringing everybody on the same page, some theoretical background. So I guess we all know what dominance means. It's just a dominant strategy has the property that no matter what others end up doing, it's always better than any alternative strategy. So once you've figured out your dominant strategy, there's no need to spend any thoughts or mental effort on trying to predict others' behavior, because no matter what they do, you'll do best. Strategy proofness as a property of a mechanism just means that mechanism implements something in dominant strategies. Now, what's the notion of obvious dominance? So a dominant strategy is obvious from an extensive game form. As long as you've been following that strategy, it will always be the case that even if the worst happens, when you follow through on that strategy, you still do at least as well as with any strategy that deviates there. So even if you get totally confused, you don't compare strategies case by case, but even if you're very confused, you will never reach a point where you think, oh, a deviation is profitable. Okay, that's kind of the idea. In that sense, it relaxes that contingent reasoning. And obvious strategy proofness then just means implementation in obviously dominant strategies. For the particular problem we're looking at here, where there's a single object that you want to allocate among a number of people with private values, Cheng-Wu also provides a characterization. Basically shows that this requirement of having dominance obvious to everyone tells you that you should run an ascending clock auction. Okay? Now let's just think about why the seal bid second price auction is not obviously strategy proof. So there, it's a static auction. Everybody submits their bid at the same time. And then the person with the highest bid gets the prize or wins the object and pays the second highest bid. So there's just one decision I make. And if I bid truthfully, the worst that can happen is that I don't get the prize. Now, if I think, okay, maybe I should consider a deviation to, say, bidding twice my value. The same goes if I bid half my value. What's the best that could happen under this deviation? The best that could happen is everybody else bids zero. I get the object for free. So that if I'm totally confused, I might think that's a good idea. So it's not obviously dominant to bid my value here. Now, how about the ascending clock auction? There, it's a dynamic auction. There's a public clock price that starts very low and then slowly increases. And at any point, you decide whether to remain in the auction or sort of irreversibly drop out. There, it's a dominant strategy, as I said, to stay in until the clock price hits your value and then drop out. If you follow that strategy, the worst that can happen at any point is, well, you also don't get the object. Okay? You'd never lose anything. Now, however, if the price is below your value, you should stay in. Okay? Now, what's a deviation there? A deviation would mean you drop out. What's the best case? Well, there's just one case, you don't get the object. It's certainly not better. Okay? Once the price goes beyond your valuation, the best that could happen if you stay in, if you deviate and stay in, is that also others stay in longer and you don't win the auction, because if you win, you actually lose. Okay, so thereby here, the staying in until your value is actually an obviously dominant strategy. Okay, let's spend a few words on how to test this theory, what kind of predictions it makes. So the domain of the theory is that of strategy-proof mechanisms, or extensive game forms, and sort of divides this space into those mechanisms where dominance is obvious and those where it's not. Okay? Now, as a test, you would compare mechanisms, one that sort of solve the same problem, one where dominance is obvious, another where it's not obvious, and the prediction would be that when it's obvious, behavior is significantly more in line with playing the dominant strategy. Okay. It's worthwhile pointing out that it's sort of not a theory of behavior within any given mechanism, but the prediction always concerns comparisons across mechanisms. So it's not supposed to explain what kinds of systematic mistakes people make. The idea is it captures something fundamental about how people, about strategic cognition, or cognition in a game, that avoids whatever mistakes people would make otherwise. Okay, now some issues that we sort of, when we thought about this, some issues came to our minds, which is sort of, it's a very complex and rich domain. There's many comparisons you could run, and in any comparisons, there's multiple aspects that vary simultaneously. There's always the question, what actually drives behavior and how informative is any given comparison? So to take an example, the sealed bid second price auction, your action space, you can make all various bids, whereas in the ascending clock auction, it's a dynamic format, and you always make binary decisions. Is it just about making binary decisions? Is it just about making dynamic decisions? It's hard to say. Okay? Moreover, typically you would run this comparison over several rounds, and already after the first round, what people have experienced is very different. Okay? So these are issues we want to address with our experiment. So we also replicate sort of the comparison between the 2P and the AC auction that I already explained. The ascending clock auction, as it's basically always implemented in experiments, it also provides theoretically irrelevant information in the following sense. The clock would always show how many people you're still competing with, how many people are still in the auction. It's theoretically irrelevant because you know what your value is. It shouldn't matter, but practically you can think about why it might actually matter, and we'll see whether it does. In any case, we also implement so what we call the blinded ascending clock auction, where that information is absent from the clock. So bidders never know how many others are still in the auction. What they do know is as long as the auction is running, somebody else is still in the auction. That's important. Then we also, the other sort of potential confound we want to address is that of feedback. So here we run also two additional auction formats that are sort of hybrids between a clock auction and a static auction in the following sense. Bidding is exactly as in the sealed bid format, so it's static auction. People just submit bids. After bid submission, however, we run an ascending clock auction. This auction is one that people would just consume passively. They couldn't do anything during that auction anymore, but it would just sort of resolve the bidding like an ascending clock auction, where the bids that people have made act as sort of automatic exit prices. Okay? So this ensures that people would always see a similar feedback. Yeah? So they would have the same chance of learning from the clock as if they actually acted in the clock. Okay, so we have two versions of this. One where this sort of passive ascending clock auction also doesn't show how many bidders are still in there, and one where it does show how many bidders are still in there. So the idea is now to say, okay, in this comparison of 2P and AC, we'll probably see that AC does much better. People are much closer to dominance. And if we turn that, say there's 100%, we scale this to 100% of the difference, and then we want to know how big is the contribution of just presenting the clock after bid submission? How much is the contribution to the reduction in mistakes that we get from dynamic bidding, which turns dominance obvious, theoretically, and how much is due to providing live dropout information? And here, we also have the dropout information. It's different because it's not live. You cannot directly respond to this information. It's just part of your feedback. Okay, but okay, so that's what we do. These two are dynamic, strictly speaking, dynamic auctions. These three are static auctions. They're all equivalent to 2P. It's exactly the same thing, just what changes is sort of the feedback.
There's another dimension which is around learning. Are you going to talk about that as well?
Yeah, definitely.
It seems like the passive story is going to rely on learning.
Exactly, and we'll also be able to see to what degree that you whether this is through learning, it's just about faster learning, or whether it's something that happens immediately. Okay. As all these experiments, we let people play multiple rounds of those. Okay, and so aggregating over all those rounds, and I'll give you more details later. Here's the decomposition. So basically, here this is 100%. So if we move here and add up the numbers, it's 100%. Actually, we get roughly 40% reduction in mistakes or deviations from dominance if we provide this live dropout information, which is theoretically relevant also to obviousness. Now, of the remaining, so of 60%, almost 50% of the reduction is due to seeing the clock passively. If you then let them actively bid dynamically on the clock, it just adds sort of another 12%. Okay? So we could say we get almost the benefits of this obviously strategy-proof mechanism just by showing people the clock after bidding. Yeah?
But are you going to show us another view of this where you just look at the initial behavior? I'm assuming this is after.
It will come. So this, as I said, this is the big aggregated result. Now let's look into detail a bit more. Okay, where these numbers come from. Yeah?
You're saying we take the benefit we get from the clock auction is 49 plus 12 plus 39.
Yeah, so the benefit, this is the details will come, but it's sort of, we measure absolute deviations from the dominant strategy, and we aggregate over all the rounds that we let them do this, and we sort of measure 100%, and we just see how much of that is do we get mistakes reduced here compared to here, where we normalize this to 100% in terms of the 100% difference between 2P and AC. Yeah. So certainly this one does better than all the others. By the way, so surprisingly, even when the dropout information is just part of the passive feedback that people, or the feedback that people get, it's actually worth 25% on that scale in terms of. Yes, so we'll come to that. Okay, just what did we do? We basically replicated Cheng Wu's experiment using sort of what's available publicly online. With minimal adaptations for the new treatments. They're very similar to the original benchmark ones.
My sloppy code.
You can talk to Eve about that. So we had subjects bid for money prizes worth up to 130 euros in groups of 4. We used affiliated private values just like Cheng Wu did, where sort of there's one draw that's for the group, and then there's another draw that's individual, and each person's private value is the sum of these, so they don't know other people's values, but with affiliated private values, they have sort of the idea it's not very far away from their own. So group value was the draw, uniform draw from the range 10 to 110 euros. These private adjustments were drawn from 0 to 20 euros, uniform. Okay, and we actually used the same sets of value draws as Cheng Wu used in this experiment. We had 20 auctions per session, and all of those counted. So it's very high stakes, and if somehow they could have bankrupted us very quickly in this experiment. The first block of 10 auctions was the standard auctions.
Isn't it a lot of money? For
Yeah, we wanted to do exactly what Cheng Wu did.
I'm using roughly the same stakes as the Kegel-Harstad-Levine experiment, so we can keep blaming back in history.
I'm asking because in the RSD experiment it sense,
Oh yes, although there's another treatment of the RSD that is much higher stakes.
but still an order of magnitude lower
Yes.
than this.
Yes.
Okay, so the first block of 10 rounds was standard auctions, just like I explained them. And then, so exactly what I explained earlier, the rules of the game. Now, the question is more what's the other auctions, which is the...
Explained 5 auctions before.
Yeah, exactly. The first 10 for each format are exactly as I explained. Now, the second block are a little perturbed versions of those, where in order to win, you had to outbid the second highest bidder by an unknown random amount X drawn from 0 to 3 euros beforehand, unknown to the players. They only knew there would be this random amount that they had to outbid. It doesn't change anything. You should still drop out at your value and so on. But it makes things a bit more obscure, and the idea of that was that, you know, maybe there are differences across formats in how familiar people are with them, and that way you would sort of level the playing field. Right? But it's important to note that in all cases these auctions were run on people with 10 rounds of experience with the standard version. Okay. Now, the average payment in our case was 24 euros. Sessions lasted between 75 and 90 minutes. We had we had around 70 subjects per treatment. Okay, so here, first picture. Here we just look at the benchmark treatments, 2P and AC, 2P in orange, AC in black. Here we have the left column is the standard auctions. Right column is the second block of 10 rounds, the X auctions, and here we have the rounds. Okay, the first 10 rounds, second 10 rounds. On the top we have our data, bottom we have Schweighofer-Kodritz's data, and what we measure here is the mean absolute deviation of bids from values where we only use non-winning bids because we don't have winning bids in the dynamic format. Basically, all this is supposed to tell you is that the replication was successful. Yeah, patterns look very similar. Okay, so this is quite robust. So let's look at our data. What's there to see? Well, right from the beginning, AC. Yeah.
Stay in the same treatment across the top?
Yes. Yeah. Exactly. So you're either always in 2P or always in AC or always in 2PAC or. Mm-hmm. Here is only these two treatments. The other three, they're to come. So right from the beginning, AC does quite better than 2P. People are much closer to the truthful bidding. And what you see is after just one round of AC, people have figured out what's there to figure out for them. And already after the second auction, it's basically quite flat.
Is this the same graph as the top one before? In the previous slide?
Exactly. This is our data. This is with Schweighofer-Kodritz's data on these two treatments. So now, since the replication was successful, we focus on our data. Yeah, right. So they very quickly learn. Already after in the second round, they've learned it. Whereas in the seal bid format, they do quite a little bit worse in the very first round. Learning takes place, but it's very slow. Just in the very last two rounds, maybe they get close to having learned as much as in AC they've already learned after a single round. Okay.
So the X version didn't quite confuse or anything?
No.
Continuous.
Exactly. Yeah.
That was a bad design decision on my part. I should probably have swapped up standard and plus X, and I didn't think of it at the time.
For budgetary reasons, we just did the same thing, not having to swap and yeah. Okay, so then what do the new treatments look like? Here's those three new ones that we added. So in green, it's this blinded ascending clock auction. In red, it's this 2PAC auction, where there's an ascending clock auction with dropout information after bid submission, and in blue, it's 2PAC B. And what we see is, well, in the first two rounds, the ascending clock auction does somewhat better, but from round 3 onwards, they're very similar. The only thing, maybe there's a slight advantage for 2PAC here in red in the standard auctions, but in the X auctions, they're all very similar.
What's 2PAC again?
2PAC is the one where, so it's like the 2P auction, except that after bid submission, they watch an ascending clock auction with their bids as automatic exit prices. Exactly. Okay, so now how does this relate to the benchmark treatments? It's right in the middle. All right? So learning is not as fast as in AC. It's a bit slower for all these three, right? But towards the end of the standard auctions they're very similar, and in the X auctions they're indistinguishable, basically. Okay, so apparently...
There is a lot of difference in the first round.
Yeah, exactly. So in the first round, they're
There's much of the original finding in Schweighofer's experiment.
exactly. So that's the idea. Exactly. So initially, these ascending clock auctions do significantly better in the first round. Learning takes place very quickly in AC, but not in this other format. It also they learn quite a lot, but then they stay above the AC auction. And if you compare the other ones where they also see a clock, but just as sort of as part of their feedback, it's basically the same. Yeah.
So just to make sure I understand, had Schweighofer run only one round, you would have said basically obviousness explains the entire results, right? If anything, your treatments make it even, they go in the opposite direction, it's probably not significant.
What do you mean is not significant?
The first round is probably not significant that your treatments actually increase the difference between OSP and SP.
Ah, okay. So the additional ones, yeah, exactly. That's right. Yeah.
So in the first round, you would have just said.
But let's look at so far we just look at absolute deviations from dominance. We don't look at what actually underlies those deviations. What kind of mistakes do people make? And that sort of is the next step. But the point is, people initially they do better in under the sort of obvious dominance. Very quickly, if they see a clock once or twice, they do as well, unless they actually also get this live dropout information. Okay. Now we want to understand better what's actually going on. Before, let me summarize. So basically, if we compare ACB and 2PAC-B, except for the very first two rounds, you obtain the benefits of obviousness just through that feedback through the clock. Initial behavior versus learning, well, we don't see an instructions effect, so to speak, but we see a very fast learning effect through the clock. We can't, as I said, the X auctions come after 10 rounds of experience with the standard form. It's unclear whether they really say something about differences in familiarity. What we can say, though, if you're worried that people are more familiar with the dynamic formats, and sort of that's why they do better, that's a valid concern because you learn very fast from the clock. If you think feedback framing is, of course, that matters. I think it's just a reminder how much it may matter, and that we should, in practice, pay a lot of attention to that. Okay, dropout information, theoretically irrelevant, yet you see it has strong behavioral effects. Is it a puzzle? Well, let's look at that in more detail in terms of what mistakes it prevents. So here's, let me check. So let's look first at, so the point of our structural analysis will be to kind of capture more than just deviations from dominance, but also look at the whole distribution of bits. Okay, so here's the distribution. There's a lot of information here. Let me guide you through. So here we look at, to make everything comparable, we look at bits minus values. Okay, so here in each of these pictures, on the x-axis, we'll have in the middle we have a 0. That means bit equal value. To the left, a negative number means you underbidding. To the right, it's overbidding. Okay? Each column corresponds to a auction format treatment. We also include Schweighofer's data here. So you can compare these two. These are the same sort of auction format here for Schweighofer, here for us. Same here, ascending clock, our data, ascending clock, his data. Here we see these histograms of relative bits minus values. First row, the first 3 rounds of standard auctions. Second one, the last 4 rounds of the standard auctions. And same here for the X auctions. Okay, so this is of early behavior, late behavior for standard auctions, early behavior, late behavior for the X auctions. Now what's worthwhile pointing out? Well, first of all, the replication was successful at an enormous detail. If you compare these distributions, they look very similar. Second, initially, the major mistake people make is they underbid. this is not kind of the intuition that we have about the sealed bid second price auction, but even here, there's a lot of underbidding. Now, what happens then? In all the formats, including our static ones, where they see a clock, the mistake of underbidding gets reduced, but the mistake that remains tends to be an underbidding mistake. Okay, so if you look here, the deviations are below the true value. So this is underbidding mistakes. Only
True in Shenmu's data without the clock. This is not an effect of the clock.
no, it's not true for the. Initially, it's true for every treatment, also in Shenmu's data. With experience, what kind of mistake do people make? In all formats where there's a clock, they get better, okay, but the mistake that remains, it tends to be an underbidding mistake. Only in the 2P, there, they start overbidding and they don't learn not to do it. Okay, so if we look here the mistakes are concentrated above the true value. Yeah, but wherever they've seen the clock, tends to be an underbidding mistake, with one big difference, namely that in the AC, where they see how many other people are still in when they're bidding, they don't underbid so much. So they go closer to their value. So intuitively, if you're not sure what you're actually doing, you get worried, oh, I might make a mistake. Maybe I should move out. If you see that there's some other people still bidding, you're a bit more, you stay in longer, okay? You're not so worried about a perceived mistake here. Okay, so what we do then is we look at sort of the actual incentives that people face in these formats, so actual expected payoffs. We normalize bids to relative bids, and we sort of estimate a model of stochastic bidding behavior as a function of sort of the actual incentives, sort of with logistic errors, where the idea is, okay, so you make mistakes that are more costly less often, or less frequently. Okay? And we add some parameters to try to operationalize some idea of obviousness of dominance as follows. So let's think about sort of the natural model for the static format for the 2P auction. So there, let's say pi of A is sort of the expected payoff of bidding A, where A is sort of in relative terms to your value. Then the probability of making a certain bid is sort of is modeled like this, where sort of you, if the payoff is higher, you're more likely to make that bid in relative terms. There's this coefficient lambda, it's the usual sort of precision coefficient. If it's very high, you're very precise, you're not noisy at all. And so that's how responsive you are to actual expected payoffs. And we add these constant terms here for as a sort of as a weight you put on your dominant strategy of of sort of bidding your value relative to a deviation beyond what expected payoffs warrant. So it's kind of an additional weight beyond the expected payoffs you put on your dominant strategy, and we'll estimate these. This is sort of somehow how obvious is it that underbidding is a mistake? How obvious is it that overbidding is a mistake? All right. So this is if you just select based on expected payoffs plus these extra weights. We also consider sort of a dynamic perspective on bidding, where the idea is you go through possible bids starting from low bids, and you always think about, well, should I bid up to my true value, or should I make this very bid? Okay, and so the actual incentives correspond to the foregone expected profit payoff when you sort of bid too low. Okay, plus of this extra weight here, and sort of you make this a sequence of binary decisions. Should I continue bidding, or should I just bid this amount? That's the natural model, I think, for the dynamic auction. But you can also think that even in the static format, we also allow people to go through that just in their heads. So people could also just think, okay, I started at a low bid and now decide, well, do I increase it or do I make this bid? Okay. And so if the probability of making a certain bid just corresponds to the probability of raising it in your bidding R, raising it R minus 1 times, staying in. Okay. So we fit both models to every format and see what the data tell us, which is the model that fits behavior best, and we estimate these parameters. Right. That.
Question about how you do that in the case. I mean, you don't always observe what somebody's bid is in the AC case.
Oh, we don't observe the winning bids. Yes, there we have to compute these. We have to impute winning bids, and we do so. We say it's either the winner's true value. If that's less than actual the second highest bid, so to speak, we take that plus 1 increment. That's right. There we have to impute that. Okay, so what can we answer with this model? So we can address the question whether actually people, do they respond to actual expected payoffs? Is the static perspective on how you choose your bid more, does that fit the behavior better, or is it more this dynamic thought process that fits better? Ignore the second point. I didn't mention anything about that. And the other question is, does the sort of dominant strategy receive an extra weight beyond what expected payoffs tell you? And we allow the different parameter for underbidding versus overbidding. Okay, and finally, of course, how do these effects depend on the auction format? So what we find is initially actual monetary incentives don't explain behavior at all. So there's the precision parameter is not significantly different from 0. Then it becomes significant, and in terms of how people choose their bids, actually in the sealed bid format, plain 2P, there the static model where you just consider all your bids and choose your bid based on sort of expected payoffs plus these extra weights, that fits best. Whereas in all of the other formats, even the sort of where you bid statically but then you see a clock, the dynamic sort of perspective on how you choose your bid fits best. Meaning, so if once you've seen the clock, you start thinking like, okay, you think about your bids starting with low bids, and you think about, should I increase it or should I stop here? Right? And that sort of natural model for the dynamic auction actually also fits behavior best for those where you don't actually bid dynamically, but you see the clock. Now, what about sort of these extra weights on the dominant strategy? Well, dominance sort of is obvious, but it's more so, and actually only so for underbidding, and it's sort of most obvious in the standard AC. Otherwise there's no differences. Okay, so sort of what we conclude from this is that behavior is quite well organized, except for the very noisy first two rounds or so. It's well organized by sort of the actual material incentives they face. The precision parameter that we get is the same. We estimate it to be the same across formats, and no significant differences across formats. So $1 is worth $1, a euro is worth €1 to everybody in every format. And so we operationalized obviousness here for this context as sort of the extra pull towards the dominant strategy beyond the monetary incentives. And we would think that this tells us that seeing the clock resolve the bidding changes the way you think about how you choose the way you think about your incentives and how you choose your strategy. So it does. So it changes this way of thinking to the dynamic kind of should I increase incremental way of thinking, also in the formally static auctions. Now, if you think about the stochastic choice model, if it's always this should I increase or should I stop here, should I increase, should I stop here, this sort of mechanically produces a tendency towards underbidding, because as you approach your value, it's basically a coin. You basically go to a coin flip because payoff differences vanish. Now, what counteracts that is that bidders quickly realize that underbidding is dominated, okay, but they never really realize that overbidding is dominated. So that means when you statically look at your bids and choose from the static perspective, because you don't see that overbidding is dominated, so you make these overbidding mistakes. Whereas for the underbidding mistakes under the dynamic perspective, so that's mitigated because you see, oh, underbidding is dominated, so that counteracts that. And only in the standard AC auctions, this underbidding, the slight underbidding mistake that remains also goes away, so to speak. And the interpretation would be that if you see others are still in, you also have a tendency to stay in longer. Okay, so conclusion. I guess I don't need to summarize. I think maybe a bit provocative, but dominance seems theoretically very appealing, but it's practically not so special, in the sense that people don't approach a mechanism thinking in terms of dominance. They don't look for dominant strategies, so they won't find them. They don't think in those terms, so they need to learn it. All right? Learning should be simple when there's no sort of, it's not about strategic issues. It's just a dominant strategy. But there's still feedback, also how you frame the feedback is crucial for the speed of learning. If you do it the right way, people very quickly figure out the dominant strategy. If you don't, they don't. All right? Now, theoretical obviousness, here the dynamic bidding seems to help learning. It's also not, though it's not necessary, you can just show them the clock and they figure it out. As I said, regarding initial play versus learning, initial play is not clear. Potential differences in familiarity may have large effects, but we don't know whether they exist. As a general point, obvious strategy proofness is not generally feasible and may also sometimes be not practical to run dynamic mechanisms. So these kind of things are separate aspects of design choice, so also of independent interest. At the same time, framing is quite unavoidable, seems a quite powerful tool. We sort of would take away from this as a suggestion is sort of small-scale dry runs before large-scale implementations of mechanisms where people can play around with them, and one sort of would be interested in seeing what kind of feedback helps people figure out how their choice affects sort of the outcome in the mechanism. And that would also be a suggestion that applies to the medical residency match. It seems advice doesn't work so well. Explanation also doesn't. Maybe if you have them play a mini version of the algorithm where they see how their own report affects what they get, would help them see that it makes sense to submit their preferences truthfully. Okay, that's it. Thank you. Yes?
When you play a repeated game, playing a dominant strategy repeatedly is not dominant.
That's correct. So the assumption that's always, so we follow sort of the standard with this qualification. We just assume people don't view this as a repeated game, but sort of narrowly consider each game in isolation. Yeah, it's the same is true with obvious dominance. Also not clear that it's obviously dominant in that repeated game.
Okay, why don't we thank Sebastian again?
Thank you.